Good morning, everyone. I'm going to present the paper entitled Leader-Follower Synchronization and ISS Analysis for a Network of Boundary-Controlled Wave PDEs. This work has been co-authored with Professor Luis Aguilar from CITEDI Research Center and Professor Orloff from CISESE Research Center, both located in Mexico. And I am Alessandro Pisano from University of Cagliari. The outline of my presentation, social network, traffic control network, and so on. Particularly, we are interested in a special type of multi-agent system where there are two types of agents, leader agents and follower agents, where the leader provide external inputs to the network in order to determine the final state of the network itself, and they are unaffected by the followers who reach consensus by basically tracking the state of the leader. There is a huge body of literature concerning many types of consensus problems and algorithms for network of agents modeled by ordinary differential equation. While the topic is much less investigated in the more challenging scenario where agents dynamics are governed by partial differential equation. And the seminal works in this area were published by Professor Demetriou. I'm giving in this slide some more recent reference concerning consensus problems for multi-agent system involving parabolic PDEs or hyperbolic PDEs. So, which are the goals of this paper? We consider multi-agent system networks where agents dynamics are governed by the wave PDE. And agents are communicating each other through a static, undirected, and connected topology. And we also have a leader agent governed by the same class of PDEs, which communicates some boundary measurement to a subset of the follower agents. We have two main goals. First of all, to show that a suitably designed linear consensus algorithm can provide point-wise in space consensus between the state of the leader and the state of the followers. We also aim to analyze a perturbed scenario where agents dynamics are corrupted by some perturbation, and we aim to show that a certain and suitable exponential ISS inequality is in force. So let us state more precisely the problem. This is the considered dynamics for the follower agents. We have here the PDE, the Newman type boundary condition, and the initial condition. And within this compact representation, vector U collect the state of all follower agents, and vector Q collect all the boundary inputs. And let me stress that these PD dynamics are open loop stable, but not asymptotically stable, which would make the consensus problem straightforward to achieve. This is the leader agent dynamics belonging to the same class of PDEs. And the control task is to enforce this exponential pointwise consensus relation, which means that the difference between the state of each agent and the state of the leader tends to zero pointwise in space and exponential in time. So the local interaction protocol we consider is a linear one and can be represented by this relation, where U tilde denotes the error vector that collect the difference between the follower agent state and the state of the leader. and M is a suitably defined square matrix that is symmetric and positive definite. Let me stress that this local interaction protocol only involve boundary position and velocity measurement. The first main result we obtained established that under the considered scenario, the proposed linear interaction law, whose parameter K1 and K2 fulfill these two inequalities, ensure the achievement of the previously mentioned exponential pointwise consensus condition for some positive constants delta and alpha. Let me quickly give a sketch of the proof. We first define the error vector variable, and we easily derive the boundary value problem that govern its evolution. Then we define quite a complicated Lyapunov functional where the two components G1 and G2 are seen undefined. However, it can be shown that with sufficiently small constants ρ1 and ρ2, this Lyapunov functional is positive definite and is equivalent to a simpler functional V0, in the sense that the Lyapunov functional V is upper and lower limited by the functional V0 multiplied by some coefficients τ1 and τ2. After some quite lengthy manipulation, we can show that the time derivative of Lyapunov functional fulfill this differential inequality, on the basis of which we derive that the simplified functional V0 exponentially tends to 0. And from this point on, by exploiting the definition of V0, the Agmon inequality and some other norm inequality, we can show that the pointwise consensus condition previously mentioned is actually fulfilled. Let me stress that the problem setup I've described only consider autonomous leader dynamics. The more challenging case, where the leader dynamics is driven by some exogenous signal Q0, can be actually straightforwardly dealt with by means of a slightly modified version of the linear interaction protocol, where simply the Q0 term is added to each entry of Q of t. The problem with this protocol is that it gives rise to a no longer fully distributed local interaction rule, because the input signal Q0 should be known to each follower agents, not only to the subset of followers that communicate with the leader. So we lose the main property of the distributed protocol by using this technique. Let us move now to the second problem studied in the paper. So we now consider a perturbed version of the follower dynamics, where there is an in-domain distributed disturbance F and two boundary disturbances phi 0 and phi 1. We aim to understand if the same local interaction protocol previously proposed can provide some ISS inequality relating the norm of the disturbance with the norm of the error state. And the answer to this question is positive, provided that the controller tuning inequalities are slightly modified. Here we can see the comparison between the tuning inequalities that were derived in the unperturbed case and the tuning inequalities that must be adopted in the perturbed case in order the mentioned ISS inequality is in force. And this is the second main result that established that in the considered scenario, so with the local interaction law whose parameter fulfill these two inequalities, this exponential ISS inequality is actually in force, where this notation ES represent the essential supremum of the argument function. And the proof take advantage of the same candidate function I used to analyze the unperturbed case, and due to time constraint, I invite you to take a look to the paper to get more details on this proof. So let us now see some quick simulation result involving a network of 3 follower agents plus a leader communicating according to this topology, to which correspond this particular matrix M. These are the initial condition of the followers and the leader, and actually we made 2 kinds of simulation, with or without perturbations. These are the results involving the absence of perturbation, and we can see that the spatio-temporal profile of the tracking error of agent 1 actually tend to 0, and also the vector norm of the tracking error tends to 0 as predicted by the theory. Let us now analyze some additional simulation where we have applied 2 types of disturbances with different magnitude to verify the effectiveness and the correctness of the ISS inequality. Actually, in the test 3, we are expecting deviation from the previous accuracy by 5 times, and the simulation result confirm this expectation. So, summarizing, we have provided a consensus algorithm for a network of agents governed by the wave PDE, and we have also derived an exponential ISS inequality to analyze the case where agents are corrupted by some perturbation. About future activities, we are trying to devise a fully distributed solution to the non-autonomous leader case, and we are also trying to extend this result towards the directed or time-varying communication graph case. So the presentation is concluded, and thank you very much for listening.